much more time?
Actually, 30 minutes.
30 zeros.
Yeah.
Okay. So, once you have your Keplerian elements, it's fine. But now imagine you have the Cartesian ones. That's actually what the next slide is talking about, is how are you going to determine Keplerian elements for Cartesian elements. And these are just basic formulas. I'm not going to establish them. I invite you to use them right now. You're not asked either to establish them. It's just simple trigonometry. For instance, if you have your Cartesian vector or x, that should be a y actually, sorry, or y or z, the x, the y, or z, meaning if you know your Cartesian position and velocity, then you can calculate the Keplerian elements using three vectors, h, n, and e, which you saw in the previous slide. Here you have h, and you already know h from lecture 1, it's the angular momentum vector. You have e, that's the eccentricity vector, it's pointing towards periapsis. And the other one, what is this name? N, is simply a construction, or here, the one in the middle. It's k cross h, that's the so-called node vector, it's pointing in the direction of the ramp, the right extension of the extending nodes. And if you know these three vectors, then you can calculate them actually using Cartesian coordinates. Then you can find your Keplerian elements if you don't know them. Because from time to time you know the Cartesian ones and you want to know or find the Keplerian ones. It's 6 versus 6. Sometimes you know the Keplerian ones and you want to find the Cartesian ones. If you type this in SDK, it will do it automatically for you. But if you want to know what SDK actually does, it uses these formulas. That's it. Find in the book. If you get exercise about this, I mean it's an open book exam, but you can just use these formulas. For instance, if I have my Cartesian vector and I'm interested in calculating capital omega, then I know that cosinus of capital omega, it's ni over the norm of n, or ni over n, yeah. And here you have the n as a vector.
Where does k come from?
K?
Yes,
It's one of the three that defines the reference system here.
Ah, okay.
K is just this
y
guy.
okay.
And it's the same that you already encountered when I introduced the coordinate rings.
Okay.
Basically just cookie recipes. Not so well, you can check it for your own understanding to see if you see how this is established, but it's just formulas for converting. Yeah. Then I have a whole section of coordinate transformations, which you need to do. I'm not sure I want to start with this today. We'll take this lecture and continue it later. I don't want to start now. Any questions at this point?
Sorry, I did not get the node vector. It's a momentum into
The node vector.
K cross
The node vector is k cross h.
And what are the 3 bars?
It means a definition. 3 bars means it is a definition. 2 bars means it's just a normal equation. So if you have 3 bars, it's usually you introduce a new concept. The node vector is the first time you're seeing it, whereas h you already saw it in lecture 1. It's r cross e.
Yeah.
So if you want to calculate h, it's just an equal sign.
You can always use an equal sign, but usually if people introduce a new definition, you sometimes see this sign, which means it means equivalent to or equal. It's an introduction of the definition, because you haven't seen it before.
What is h sub k? Is there number 3 inclination, cosine inclination angle equals
H.
h of k over
Where
h?
are you?
Number 3,
Number 3?
yeah, inclination,
hk, I mean, h here in bold is a vector,
yeah. So,
and it's
Ah,
its
j
k
k.
component along k. So meaning here h is the vector, and hk would be the component along k.
okay, in the ijk's.
Yeah.
Okay. And then likewise for the before ni is just
Along I, which is along ni, it's if you project the vector n, I mean again, it has an I component, has a j component, and a k. Well, it doesn't have a k.
and we don't use the j for anything except for the vector total.
Yeah.
It's weird.
And this concept of motion, h, is perpendicular to the r and v.
Yeah. Always. So h is the vector perpendicular to the orbit.
Okay, so why this is called a motion?
Constant of motion. Why is your question? Why h is called a constant of motion?
Yeah, I think that it is somehow it's not
H is
it's
perpendicular to R
perpendicular
and
to motion.
Angular momentum.
It's perpendicular to motion. So
More, it is perpendicular to the motion. You see, h is like that, perpendicular to the orbit shown in hash. And we established in lecture 1 that it is a constant of motion, which means that h is not only perpendicular to here, but it stays constant, which means it is not wobbling like that. Which means that the orbital plane will stay always fixed like that. Because if h was not constant, imagine h moves with time, so h could be doing that. Then you know that the orbital plane too, the inclination will change and everything will change. And fortunately, h is constant. Otherwise, these guys would change with time. Yeah, you know what? Let me go a little further. So I'm going to get back to this later. Just going to show you an overview where we're going. We'll do coordinate transformation next time, meaning we take our reference systems and we go from one to the other. That has to do with rotation matrices. This is the most technical lecture you get, but still. We talk about rotation matrices. We talk about successive rotations about several axes. Yeah, here we determined Keplerian elements from R and V. We'll do the other one too, determining R and V from Keplerian elements. That's here. Then we talk about time. We'll talk about solar time versus sidereal time.
What's the real time?
To anticipate, we can talk about that for a second. Solar time is what you experience when you have a look at your watch. See, solar time is, I mean, here you have Earth, you have the Sun. And in one solar day, you see Earth has turned around itself. How would you explain that best? The solar day we are experiencing takes a little longer than the sidereal day, because if you just take one rotation of Earth, let's say we are looking towards there, let's say we are here on Earth, we're looking towards the sun there. If we wait for complete rotation of Earth, it will be here. See, here Earth has done one rotation around itself. The North Pole is coming out of the plane. Yeah. So that's what you call a sidereal day, which is actually shorter than what you really have. I mean, the real thing is that what we call a day is I have a look at the sun here. It's there. Now I wait how much time is going to evolve until the sun is again there. But meanwhile, Earth has gone on its orbit around the sun a certain way, as you see here. So the solar day is longer than the sidereal day. The sidereal day is just based on the rotation of Earth, whereas the solar day is based on the rotation of Earth, plus the effect that Earth itself is not only rotating, but also revolving. See the difference between the two words, rotating and revolving.
So what we have the daylight saving?
That's what we get. So we talk about time, daylight saving time, Greenwich Mean Time, and stuff like that. Here, that's what you know. I mean, we are Luxembourg, we are at UT+1, meaning UT is what you have at Greenwich. We are 1 hour later, but all of these are solar days. Sometimes you have to convert to sidereal days. There's a formula for that, so that's the stuff we're going to see. Determining sidereal time when Greenwich Mean Time is known. Then here the stuff, did you know that Earth is the top in 2P in French? The fact that, I mean, earlier somebody was asking me, is the polar direct, the axis constant? In that figure, actually, somebody was asking me. Yeah, somebody was asking me, is it at least constant at the red axis? And I was saying yes, but no. Actually, if you, depending on what kind of missions you're designing, you need to take into account that the polar axis of Earth is actually not like that, but doing a little more like that. Like a top. That's why I'm showing it. Top here. That's what you call the precession of the equinoxes. You should know about that phenomenon. We will not go that far about it, but if somebody tells about the precession of the equinoxes, it actually, because the consequence of this precession is that the gamma there, the vernal equinox direction we were defining in the beginning of the course is not precisely constant, it changes. But here we now go really to hardcore stuff. So I want you that you know this. Likewise, as you probably know, Earth is not a sphere, Earth is more like a potato.
Yeah.
This too has some practical effects. Means that the gravity, right now we are treating gravity as constant. But if I have an equatorial orbit, let's say I have a satellite orbiting in this plane, I get a bigger pull from Earth back as if I'm in a polar orbit. So depending on what precisions I'm looking for, there's some applications. If you want to do, if you take your GPS system, self-driving cars, here a matter of meters, if not centimeters of precision is required to avoid two cars crashing in each other. So you need to have a good model of the potato-ness of Earth in order to take into account these irregularities.
This is real,
This is what Earth is. Took a whole space mission, GOSEED, to find that out. And so what you can see, so this is Earth, and on top of it, it behaves like that, meaning that the pole is doing that. So what you can see in this figure, there's a precession and a nutation. I'm not even talking about this.
You can know that it's so
Wow.
yes.
Don't you find it of late?
In some places,
For me, it's quite. It's not. It's this little figure around the waist. You have like a person who has a certain age, you get thicker around the waist, but you're going smaller. Yeah, but that's the real Earth.
So is that just a gravitational field of the Earth, or is that a real representation of what the Earth is physically like?
This is how the Earth physically looks in reality.
Do you know what the colors mean? What is the scale there that is shown? Like blue to red?
I think the deviation from a sphere. So usually they take the model sphere and they say when is it higher than the sphere, when is it lower than the model
So
sphere.
it should be more rounded than that.
This is so weird.
Yeah.
Yes.
And
Like, did someone ever took an actual video from like far distance, like the Earth rotating in like a real image, or there's no data
if you
later?
go far away from Earth,
You cannot see that.
you wouldn't. I mean, of course, Earth is so big.
Yeah.
I mean, if you're on the ISS, you are
Don't
not far
see
away.
that.
You just see. I mean, you don't
Yeah.
see it from far away. The
Yeah,
perspective
yeah.
is not good. And if you are at the perspective far away that you could see it, then you don't have enough light anymore. But the gravitation, there's a mission GOSA, I think you can look it up. It actually determined that using a rather refined system, and that's what they found. And now this is again used. This was used as an input to the whole GPS. This is as input to the GPS system to model Earth gravity, which is used because the lecture is about orbit determination. You need to know very precise knowledge of the orbit of your. There's some missions where you need to have precision, like GPS. There's others where you really don't care, like a CubeSat mission, and not even. Yes.
I was talking with Blair about this. Since gravity is a radial force and planets are formed by high gravity regions accumulating debris, why would it be so homogeneous in shape?
But isn't it kind of quite homogeneous? I mean, if you think about it, it was accumulating. Now we're talking astronomy, the formation of the solar system. There's probably one big star that was formed, and then you had, let's say, bunches of elements ejected or not, that did not make it to become part of the star, so they cooled down, all in a disk, let's say, more or less a plane away from the sun, and then they cooled down, and it became a planet. I mean, I don't know. Nature is never perfect. It's close enough to be modeled by a sphere, but of course, if you have a real look at it, it's not.
This model does not include the oceans. So if we fill up the water, does it become? It looks like a sphere.
I think it. I would have to check, but I think it includes the oceans.
But can we have oceans which? I mean, the surface has to be equidistant, right? No.
Oceans are moving.
Not with the atmosphere. I mean, the level.
Would
I
it?
mean, can
I
it be
mean,
such a big deviation?
what is fixed by gravity now? If you're on a perfect sphere, if you're in a potato, it shouldn't matter that much. I can look it up, but it should be with the oceans. And even if it was no, and even if it, I'm pretty sure it is with the oceans. But even on top of it, what I wanted to tell is it's not only that. I mean, now take this guy and spin it. Huh?
Yeah.
It's even more complicated than just that, because then you get this effect.
Yeah.
And you see one period of precession is 26,000 years, then you have a period of nodding, meaning that mutation. The period is 18 years. So depending on how serious you are and how precise your mission needs to be, this matters. We get that. But
The period of the pole is 18 years? The period that the pole takes to...
the period of doing one of these little wavy ones.
Oh, the wavy ones, okay. And the 20,000...
And the period of doing one circle like that.
26,000?
26,000 years.
Oh, okay. Okay. Yeah.
But sometimes...
Yeah.
I need to talk about I had in mind
You will last
exam. I mean, if you depends on the exercise. I mean, right? If I knew that you could use SDK, I could do an SDK exercise. But SDK will not help you in, for example, if the exam question is like explain the capillary elements. SDK will not help you.
Yeah, no, but just like computing the cosine.
Yeah.
And macro.
Yeah. Because I just need to know, do I need to go back calculator? Okay.
Yeah. If we were not allowed to use a computer for calculations, what kind of calculator should we have?
I'm going to talk to Tony. I don't want to say anything related to the faculties of the world. You will start this like that. If it is by me, it is just to use the computer that you want.
And do you have any feedback from our laboratory?
I received the first contract, so I have looked at your activities, but I will support it.
I can.
Yeah, I have a question about the exercise because I think there was an exercise that we had to calculate we had not the vectors, but we had the module just the value of R and V, and we had to calculate H, but we didn't have angle. So then it's not possible, right? I want to like.
Should be. I mean, I'll have a look, but everything in the exercise is possible.
Okay.
I don't remember myself.
Yeah, because there was like two exercises. There was one that we had like the vector R and V, and then we just do cross multiplication. But then when we just have the then we need the angle between, so we can like do R multiplicated V multiplicated, I think it's cosine.
We'll discuss about the exercises next session.
Okay.
And we'll continue. I mean, I sent you all the material already today, but we continue with this lecture for one more session. So how much more minutes? 5. Let me show you in orbit determination. So this is the second part. I mean, the first part, as I was telling you, was just basic input for you to, tools you need to understand to do orbit determination. Then just to show you a bit why orbit determination is needed, you have a number of applications and numbers of precision levels. For instance, you can imagine the topic of, that's a topic I have been working on, space debris. And for instance, you see here's a nice video over the last 50 years of the number of debris in orbit. Maybe you have seen it. It starts with 1957. And then over the years you can see how much more, you see at that time the orbit determination was simple, you just had 2 satellites in orbit. But then the time here is now how more and more satellites and debris populate our Earth, and you can see how problematic it becomes. And today we have in the, I think, 6,000 satellites, over 30,000 debris of size bigger than 5 centimeters, over 100,000 debris smaller than 5 centimeters, and you need to know them all. You need to determine the orbital region, and we want to avoid collisions of the type I was showing you.
And how do they manage to launch the rocket if
Well, there's you have a whole service done for the Western Hemisphere. It's mostly the Americans who have radar. I actually wanted to show you that they have radar sites. That's what the Europeans are doing. So when I was working on that, I was mainly interacting with this French ship, but then you have, this is just the European perspective. Then you have the German ones, that's a radar in Western Germany. And here you have a whole radar network and telescope network of the US. To answer your question, when there's a launch, this whole system checks if it is clean to go. And then if that is checked, then you launch. But even if you're in orbit, you have a permanent, right now as we speak, we have a big team over the world, trying to avoid that we have crashes like the one here, which happened also already. A number of times.
What's the speed around? I mean, it depends.
The speed.
The speed of the debris.
We calculated it in the last lecture.
Yeah.
What
No,
was
the debris. I mean,
It's all the same.
Yeah,
Whether it is an elephant
Yeah,
or
correct.
whether it is a debris as small as this,
yeah.
it has the speed it has, and it's bigger than the bullet of a gun. Depending on the gun, I don't know. Gun. It's the imagine you have I don't know 100,000 little objects like my
How,
thumb.
if it's even possible then with radars to understand if they are like this so fast?
Yeah, but then it is in you enter the technology area of good radars, and that's a strategic technology when not every country has it. I mean, who is good in radar? It's the US, it's the Russians, it's China, it's Japan, maybe Europe. What we have in Europe is basically two systems for space debris or space objects. It's the French, mostly with that Le Mans, which is good because this guy can move along the oceans and track into areas where this guy can't. But if we were not supported by, you see, the US has basically agreements with, of course they have not here, they have a station in Greenland. I mean, if you remember, Trump wanted to buy Greenland from the Danish. It's one reason. You will always want to have stuff close to the poles. Because if you know what's going on and the others don't, it's good. But they also have stuff on this little island Ascension. They have an agreement with Australia. That's Guam, another island under American influence. So this is just the European side. Then you have, of course, the Russians and the Chinese and a number of other countries who have their own system. But all of this just to get a full knowledge of what's going on. And all of them are doing orbit determination all the time. That's why the topic of the lecture was orbit determination. I'll show you next time actually how you do it with a radar. See, here is orbit determination from a single radar observation. We're using a reference system we have been introducing today, and we try to understand how this is done. Thank you. We have a participant list somewhere.
Oh yeah.
Let me know if it is too complicated or too easy.